So I had some specific questions from the Peking lab. And the reason I'm going to go through that is because the data sets are very interesting and exemplary of the issues that you'll encounter in general. I do know that the Hackett lab in particular is dealing with lipids, lipid vesicles, not lipid vesicles, but you know, nanolipid discs and stuff. And those issues are peculiar in some ways. But hopefully you still get something out of this. This would be sort of examples of proteins in solution, or you know, macromolecules in solution that have constant density, electron density. So they're homogeneously density. The challenge with lipid particles is that the electron density is not homogeneous. The phospholipid head groups scatter way more than the aliphatic tails. And so you see mostly the head groups. That's a particularity of that kind of a system or detergent system. All right, so this is the kind of data that you're likely to receive, and Catherine gets major props for helping me put these together. There's some nice things in here that will help you really give a good scan. And again, I'm just going to briefly go over them. There's a directory called sample cell picks, so you can quickly look at the sample loads. And I'm going to do that here. And so this is our needle, which has picked up your sample and transported the sample to the X-ray beam. That square box is the liquid, your sample liquid, and X-rays are being shot through that. You know, sometimes you can look through here quickly, and I'm moving through them, and you'll see bubbles or variations. Like there's a bubble right there, right, for B6 that, you know, would explain some phenomenon that you might be. And you can look at a gallery view of this as well. So that's one thing you have in there. You also have a file called avgraphs, which looks at the scattering across your samples, both a buffer 1 subtracted from your samples and buffer 2 subtracted from all your samples. And ideally, all of them will agree with one another. But you can pick up things here. You can say that A2's got some issues, so I got a little bit, there's something about A2 where buffer 1 didn't quite match up with everything else, so let me take a look at that a little bit in more detail. So just a little bit of warning signs, and you know, again, you can scan through these. And so the samples I'm going to go through, and again, pardon me, Peking Lab, if I'm saying something that's top secret. The study there is some protein that binds some other protein. Hopefully that's general enough that it doesn't disclose anything anything secret. The wells A2 through A4 are the complex of protein 1 and protein 2. A7 is protein 1, so you can see that it's that it has a very different scattering profile. And then all the way in E is the protein 2 by itself. But anyway, we're going to go through those samples. And here are just sort of the results from the processing. And again, you're looking for differences between buffer 1 and buffer 2. You know, how things went. So it's a general collection thing. So look through those. You know, for example, here's another like little issue that you can see immediately. All right, so closing that out, and I apologize if things are slow. My wife is teaching AP chemistry next door via, we'll close up, and my son is studying something else next door to that. Okay, so that's that. You'll find subtracted and unsubtracted files as well. So I'm going to move into the subtracted directory. And there you have all your data from all the wells. If you go in further into each well, so I'm going to go into A2 results. You will see generally, you should generally see 3 files. You're only seeing 2 here. This is the the buffer, the first buffer subtracted from your sample and the second buffer subtracted from your sample. And typically you'll have an average here, but sometimes it didn't get output in this case, but there'll be an average sometimes. All right, so each well will have buffer 1, buffer 2, and generally an average. And then if you look inside of buffer 1 and buffer 2, or buffer 1 here, you will see your subtracted data. So that is buffer 1 scattering curve subtracted from buffer 2 subtracted curve. And there are 33 frames here. And those 33 frames are generated because we expose the whole sample for a full 10 seconds, but the camera that's capturing the data is framing that data at a 0.3 second intervals. So that's a way to determine when radiation damage is occurring. And it's impossible to know ahead of time when it would occur. So you might only be able to use the first 5 frames, or you could use all the frames. So that's why there's a whole series. And I'm going to show you a tool of integrating that stuff. Okay. So all your directories will have that. Also, there's an unsubtracted directory. And what this folder has is not only your samples, but it also has your buffers. So in these cases, no buffer was subtracted from the sample. They're just the raw curves. Okay. And you could plot them up. And some tools out there like Scatter or Primus, they'll enable you to you do the subtraction on your own. So you can subtract the buffer curve from your sample curve on your own. But usually we would recommend using the subtracted variants if they're looking good, unless you're doing something weird. And again, I think I remember from the Hackett lab that they put a different buffer in buffer 1 and a different buffer in buffer 2, and they're doing some funny subtraction there. So the unsubtracted files allow you to do that. All right, so that's that. Catherine's also put in a Excel spreadsheet that has made some comments there. And there's also an analysis of the Grenier region here, which I may not show, so there's some neat things in there. I'll briefly show you. So I just looked in that RG thing. Basically, it's pulled out the RG region for every curve. And sometimes you'll, it would be like figure 1 for a SAXS data set. Okay, so you have that data there. And I could do something like plot all of these RG curves. Let's see, I'll just do just the first buffer for everything. And so from this entire data set, let's see what happened there. Sorry. LS. Oh yeah. So these are all the curves, all the data, all the buffer ones, and the RG region, the Grenier region of all the curves for the whole sample set. So, they tell you about, how linear. Some of them were aggregated. Some have a very small Grenier region. Some of them are solid. So again, as you get better and better, you'll understand this kind of thing. But that's there. All right. And again, you can plot those. Those are 3-column ASCII kind of stuff. So you can plot them with whatever tool you want. All right. So results. All right. So that's that. So let's go through some data here. So once you have an idea of what we collected for you, you can start pulling it down to your PC or your Mac or whatever. And hopefully you guys know how to do that. And I've already done that for some curves here. I've done that for this set. So protein 1 is A7 through 9. Protein 2 is E4 through E6. And the complex is in the beginning. Okay. So let's go here. So a tool that we've developed to help you go through those 33 frames and figure out how many files you should use is a web tool. And we do have a called SAXS frame slice here, okay? And so this is a drag and drop tool. I'm gonna take the easiest case, which is protein 1. And you have your buffer 1 and buffer 2 files here. You can drag and drop. So again, I'll just look into that file before I drag and drop. These are the subtracted.dat file. So you can drag that buffer 1 down into this drop down spot here, and it should load things up. So there occasionally is a problem with the very first frame. Sometimes the very first frame, the shutter didn't open in a synchronous way with the starting of the collection. So sometimes that very first frame is off. And you'll see that immediately in this processing here. You can remove that file, that first frame, if you need to. So what we're looking at here is protein 1, and we're seeing the scattering from it. The black dots are from the very first exposure, and the orange dots are all 33 frames put together. Now this is an extremely low concentration result, so it's not, you know, ideal, but this is low concentration. And what we're looking for here is how many frames we could use before radiation damage takes hold. So what we'll do is, so it's divided the data into 3 regions, sort of a Napoleon, like mint, vanilla, and strawberry kind of coloring. And the mint coloring is the Guinea region, and I can click on that, and I can see all 33 frames and just the first frame overlaid. And you can see that the scattering doesn't change very much, it just gets better. And so these sliders over here allow you to increase the number of frames you want. So I can slide it all the way over, and now what you've seen are 3 curves. The very first exposure is in light blue. The orange is still all frames together, and then the black one is the one I'm going to save. I'm including all 28 exposures. So here I can go full here, and you know, and usually, and I'll show you a case where, so in this case, this sample isn't very particularly radiation sensitive, or at least the noise is such that you wouldn't be able to tell. So you basically can crank things over. And again, I'm going way faster than I would if I was processing my lovely samples. I'm just doing this quickly here. So now I'm using 28 frames for everything, and that's my curve that I can work with. And I can hit download, and it will download that curve for me, okay? I think I've done some of this processing already, so let me just make sure. Let's see, yeah, I have, okay. So I've done that. And then I would load buffer 2 down, so I would hit download, and then I could hit reset, or I could resync this thing up here in the corner. And I could pull down buffer 1, or sorry, buffer 2, and I could do the same, doing the buffer 2, pull them up. Yeah, and while this is loading, the one thing I definitely wanted to say, I'll make a plug here. Please remember to cite the Beamline when you publish. It's how we stay afloat, and you know, really appreciate, and also really hold us to the fire if you're seeing something that's not working for you. We're here to help you guys, and your feedback is very important to us. So please, the more you guys can feedback with us, the better. So again, I got my buffer 2 here. I'm going to do the same, cranking over. Got my files. I'll hit download, and now I'm going to go to scatter. Okay, so now I've got 2 folders, buffer 1, buffer 2. I've decided that I can use all of them. There's no radiation damage, so I can go to scatter. And scatter, well, let me just open it fresh. So of course, I just downloaded the most recent version, so it's in my downloads file, super well organized. Again, we are scatter devotees mostly, because scatter did start at SIBYLS. But unfortunately, this isn't, the SAXS community isn't black box yet. We're not, Phoenix yet. So we do drift back and forth, and you will see everyone do this differently at the moment. So there's nobody who's taken a monopoly on the processing of the data yet. And there's things I love about scatter, and there's things I love about AdSet, and there's things I love about other programs. They're all amazing programs written by scientists just like you and me, not by professional companies. So, that has all of that stuff with it, right? All right. So I'm going to go back to my downloads. So I've used scatter and the frame slice, and I've generated my A2 files. So from buffer 1 and buffer 2. So there they are. And I can drag and drop them into scatter. And where do you get scatter? Let me put that 2. Let me go. Sorry, doing a lot of SAR stuff. SIBYLS SAXS. We have scatter right here at our webpage, the newest version of it. So that's where you pull scatter down. All right, so I have just loaded buffer 1 and buffer 2 in here, and I can hit log 10 plot. Oh, it's not. Oh, sorry, A2 isn't what I'm working on. I'm working on A8, A7. Shift. I'll pull that down. Log 10 plot. So there are my 2 curves that I just compared, buffer 1 and buffer 2. I will examine them carefully, make sure they agree. I could average the 2, etc. Okay, so that's that. I'm also going to pull down the concentration series. So they did a concentration series, a low concentration, a medium concentration, and a high concentration. So let's pull those guys down. And I've just done the same thing with the frame slice tool. Log 10. And so there's the 3 curves of protein 1 and different concentrations. The lowest concentration is the noisiest, obviously. And the reason that we collect 3 concentrations is to see if there's concentration dependence. So in this particular case, you will see that the proteins in solution, they are starting to interact as you increase the concentration a bit. And that's just because they sort of feel each other and set up sort of a non-entirely random structure in solution. And that has to be corrected for. And in this case, it's not so bad. So that's awesome. In another case, I'll show you, it's pretty bad. And it actually is a different type of concentration dependence. It's the kind of concentration dependence where the structure is changing as a function of concentration. Okay. In this case, the sample is feeling other copies of itself around, and it's setting up like a pseudo liquid lattice of some kind. Okay. So how do I see that? What I want to do is, it's going to only occur in the small Q region. What I want to do is take the high signal to noise that's probably not changing very much, sort of this middle region here, and I want to scale them. Okay. So scatter allows you to do that. You can hit the start part here, and you can say, I only want to look at data from 0.07 to 0.15. So that's what I'm going to do. I'm going to hit start here. I'm going to input 0.07. And you can see on the graph, oh, let's see, log plot. Let's see, start 0.07. And guys, and then we're gonna do this one, 0.15. So I'm just looking at that region. I'm gonna hit scale. I'm gonna hit scale. You know, maybe I've taken the noise too much, but I'll definitely examine. Okay, and with scatter, you can zoom in and out. And the way you do that is by dragging one corner, holding down your mouse and zooming, just like you do with other functions. But to zoom out, and this is something that Rob, who created this program, didn't describe very well, is you hold down the left button and just flick. Sorry, hopefully that, oh, except for this is just a little bit. So I'm gonna go here, and that's the example, and then you can flick out to unzoom. So you don't have to replot it every time. So you want good overlap. Oop. I want to hit scale here. All right. So, you know, you want to make sure you picked a region that there's going to be good overlap. Maybe 0.015 is too far into the noise, so let me just back that up, 0.01. Let's do 0.01, 0.1, and 0.07. Somehow it's giving me trouble. Let me hear. But anyway, we got the scale. So let me. So then once I've scaled them together, let's add all the points back in. So I'm gonna go all the way out to 0.01, or the smallest Q. And I can now zoom into the Gunye region and see that the lowest concentration is low, the middle concentration is, you know, green, and then you got the red one, so, or the purple one, sorry. So you've got to really extrapolate to zero concentration here, so that you get the best curve that is free from this sort of interparticle interference, okay? So that's why we collect concentration series data, and yeah, what we do with it. So to correct and so you basically want to extrapolate to zero concentration using the trends you observe, and of course it's only affecting the data up until 0.07. So there's a tool, and unfortunately it's in Primus. Scatter hasn't quite implemented that yet. So you would basically do all the same functions with Primus that I just did here, and you would hit zero concentration extrapolation, and it would give you a final curve for this region. Okay, and I'm not going to go through that for the sake of time, but it's there. And I think the thing I covered here is why you collect a concentration series and how you look for the trouble. And then you plug exactly the same thing into scatter, hit zero concentration button, it'll give you a curve that's an extrapolation to zero concentration. Now the curve that's closest to zero concentration is your lowest concentration. And so what you want to do is you want to merge that new zero concentration curve from Primus with your highest concentration signal at YQ. And I'm going to approximate that by just using the low concentration sample. 10 plots. And you can see that there's I can merge this and I can get the best of both worlds, like a concentration corrected sample and the high signal to noise you would get at the high concentration. So basically I just want to overlap these. I want to clip at both ends. So I'll, let's see if I can show both screens at the same time. You know, so I'm just clipping down the data, and I just want to have a nice overlap region. So I'm just dropping the number of points here. So something like that. And again, you can change the colors of Scatter does random colors, so you can, you know, change it to be, you know, red and black if you want. Sorry, I want this one. Black. Just to make it clear. And of course, it didn't change the colors. But anyway, it should work that way. And you'll probably want to trim some of this data out here too. So anyway, we want to create a merged curve that has the best of both worlds here like that. And then you hit scale merge, or there's a variant in Primus scaled merged. All right, and then you have a scattering profile in here in your set here called the merge. This is the red curve, and it's a combination. I'm gonna turn all the other graphs off. It's a combination of your 0 concentration corrected sample and your high signal to noise and the high Q, because the concentration dependence typically only affects the Guinea region. All right, so the next step is, I'll just go through the steps here for the basics, okay? So, and Primus has tools for all of this as well. So, and you'll develop like or hate with different functions from different tools. So the first thing I typically do is I go through the volume. I'm going to find the volume of the system, and by finding the volume of the system, I'll be able to extract the mass of the system. So what I'm looking for is a flat parts in the plot at the bottom here. Something like that. So I'm going for drop in the number of points here. I'll just write 200 here. So I'm just looking for a spot that's pretty flat. And if you can find a spot that's flat like this, like that it plateaus, that means that the decay is as a function of Q is indicating a globular region, something that's very globular, something that has a sort of a very, very well folded system. Okay, so you want to find, if you have a well folded system and versus a molten globule or an unfolded system, if you have a well folded system, you'll find the exponential decay to be around 4. Okay, 2 to the negative 4 in a certain region. And once you found that, it gives you the volume of the protein. So that's in cubic angstroms right there. So that's useful to write down. And the reason that's useful to write down is later on you're going to generate shapes. Often you're going to generate shapes in sort of an EM, like a rendering program. And that allows you to have a level of contour. And for each contour, you have a volume. And so you can adjust the contour of the EM map to be equivalent to this value. And that gives you sort of a more accurate way of getting your volume, your contour. So that's that. So I have my volume. That's good. Step number 2 is to click a button here, this VC plot thing. This VC plot thing does a calculation, integrates that curve up until that region I just found with that slope finding tool. So I just click that. It does an integral, uses the radius of gyration and that volume to come up with a mass. So now I can figure out what the mass is. So I go to this merged curve and I left click on that button and I look at sort of a result summary, and it tells me that that protein molecular weight is around, I want to make sure, 13,000 Daltons or something like that. Do I have that right? Yeah, 13,000, 1.3 to the 4th. So 13,000 Daltons. So that gives me my mass. Yeah, I probably forgot to do the Guinier part, but it already did it automatically. So the Guinier part, if I hit G here, makes me find the Guinier region, which is also very important to do. But it does it automatically in some cases. But you want to help it along. So, so right there, the radius of gyration here is reported to be about 18.2 angstroms. So that's point data point number 3 or 4 right there. There is a way to also, so the radius of gyration is sort of the first moment of inertia kind of measurements. There's another moment of inertia, the second moment of inertia, that's called in this radius of cross-section analysis. And you can hit the button, and it's very similar to the other tools where you kind of find the linear region here. So sorry, you're going to go 200. You find a linear region in here. sloping up. And again, a lot of this is already in the video tutorial I have online in the YouTube channel. And it gives me a radius cross-section of 10.72. So the second moment of inertia is 10.72. And I can compare that to my radius of gyration, the first moment of inertia. And if they're similar, I can say it's a pretty spherical particle. If one is bigger than the other, then it's an elongated particle of some kind, something slightly elongated. So that gives me some other points. All right. Next, you would go for a real space function, this P of R function. And again, in this case, it's so easy, right? I mean, this is such a nice particle. So I just hit P of R here. And he's got a tool in here that allows you to just find Dmax, right? So you can hit find Dmax, and it'll go through a process. Let's see, the window. And again, if there's breaking, usually a window pops up, and of course it doesn't here. In this case, hopefully during your fresh load of this, it will, but you can also help it along. So basically you're just looking for the plot space where the P of R slides down into something close to 0. So somewhere around, 65 angstroms is the maximum dimension of this particle. This is the P of R function. Again, I hate the fact that he assigns it to be red because you can't see the fit. So anyway, here's the data, black, and here's the fit that the P of R function has to the curve. So this is pretty good. And you can also drop the number of points here and just make sure that the P of R function stays consistent. Oh, sorry, I should at least keep some of it here. But it's a good thing to do, is to check, make sure the P of R function is pretty consistent. All right, so you would do this, and then you're ready to generate shapes. So basically, the output of this step will give you a .out file, which you can now feed into the shape restoration programs. And if you've got it all hooked up properly, let's see, where are you? No, P of R. Somewhere in here, it'll do if you've got AdSet. So in order to generate shapes, you need the AdSet Suite, which is also related to this Primus thing. And you have to link this program through that in the settings. And basically, you hit go, and it'll give you a shape for the system. So that's how you would generate shapes. And there's a lot you can read already on how to do all this, so I won't go through it in complete detail. But if you have questions or want particular, we can go over it. Again, I want to save some time for Mikkel here. So that's shapes. All right. I'm going to do one last curve here, and that is one that is not so super easy. And that is the complex, actually. So that would be an A2, and that one is going to have radiation. It's going to have radiation damage. It's going to have all the lovely stuff, because when you're working with the living systems, they're never easy. So here is, let me work with the medium concentration, because again, I want to. And again, you would want to do this for all concentrations and compare all concentrations. So I'm just going to pull this over here and just do buffer 1 of the medium concentration.
Correct, 2 minutes.
All right, I'm working on it. So this is a case where that first file is bad. You'll see as I increase the number of frames here, it immediately drops down to the height. So that very first frame, I'd want to remove that one. Yeah, and I would go in and into the folder and delete it. Let me do that, actually. Sorry, Mikkel. It will be more than 2 minutes, Mikkel. It'll be like 5. So I just deleted that first file because it just got clipped, or the timing wasn't quite right when the detector started collecting and the shutter opened. And the same is true for the last file too. Sometimes the shutter will close. So here's that file. All right, so I'm going to zoom into the Guinier region. And you can see that the first frame is different from all frames integrated together. So that means that the sample is experiencing radiation damage as a function of time. I'm going to start increasing the number of frames, and you can say if I pick something intermediate, the first frame is different and the last frame is different. So I got to find my little medium range here. So somewhere in maybe just the first 5 frames or 4 frames or whatever. So I would start with the Guinier region, and then there's all these little neat sliders that allow you to go see other things. Pay attention to the bumps and wiggles. So in this particular case, you can see that even in the high Q, there's a bump out here that you want to preserve, okay? If you get rid of it by using all the curves, you're going to lose features in your data, some resolution. So you want to preserve those little bumps and wiggles. So I'm going to go for 4 here, you know, and if I go too drastic here, in this intermediate region, you can see I've developed a step function. Let's see here. Right at the change of the Guinier region and the Porod region, there's a step function because I'm using 25 frames for the Porod and 4 frames for the, so obviously you want a smooth transition between the regions, okay? So I'm gonna back that off, so that's what you're looking for. Again, if you have a step function and you Fourier transform a step function, you get all kinds of harmonics in your P of R function, which is what P of R function is, a Fourier transform of your data. So full. So those are the things you're looking for. This would be the curve that I'd be working with, something like that's using 4 frames for the first Guinier region, 8 frames for the Porod, and 20 frames for the high Q, because there's not a lot of damage out here. Okay, so that's radiation damage. And then let's look at the concentration dependence real quick. So, sorry, Mikhail. It's in downloads. And again, this is just preliminary processing, right? You know, you can get really fancy here and start, you know, building off of structures. So here are the concentration dependent series here. And if I use the same criterion as I did before, find some small Q region, let's see if scatter really crashes on me because it's been used too much. And all right, cool. Hit scale. So scale. You can see even in this region, there's some changes in angle. So let's bring everything back. See the sort of concentration dependence in the small q, and 0.3, 4, whatever. And then if you look really carefully, let's look in, you know, you can see like bumps coming in and out. So this is probably a little bit more than the concentration. And also, you know, what's really interesting is the trends are different, right? So the low concentration is red, brown. The middle concentration is blue, and the cyan concentration is the high. Sorry, maybe I didn't say that right. But anyway, so the trends aren't quite right. So there's something going on about this sample. It could be that as a function of concentration, there's more complexation going on, or less complexation, or maybe the whole structure is getting a little compressed. So, I mean, these are really good things to know about your solution state of your protein system. You know, this is, again, the living system stuff. So, I mean, what you can do, there's 2 things I would recommend in this case, because you're looking at a complex. Obviously, one really valuable thing to do would be SEC-SAXS, where you do purification at the same time you're doing SAXS, so you're separating things. It could be, though, that your complex has a KD that's very, you know, weak, and you only get the complex in high concentration. So again, you won't, you know, when you run that over an SEC, you're going to be measuring very low concentration samples, so you might not be forming that complex. So again, you can do that. You can also look at different buffer states in high throughput screen to help you formalize, you know, make that complex a bit stronger. Again, this is where we're kind of trying to understand the complexation of the system. Last thing, Mikhail, I swear, last thing. You can, if you have a crystal structure, you can feed it into Fox. So you can do a search for Fox. So do Fox and SAXS together, and you will find this web page, Fox and SAXS there, okay? And then you can either put in a PDB here, which I can't remember what was they gave you. You guys, can you remind me of the PDB here for the complex you guys got? Yeah, here it is, right. And you can put in, I'm gonna put the medium concentration in here. And it will calculate the SAXS from your PDB. So here's, oh, sorry, I picked the protein one, not the complex. But anyway, you can see that that resembles the curve we were just working on. And so, but not perfectly. Oh, let me do that again, sorry. Back, I choose the right one. It was A2, A4. Yeah, so that's the comparison of the two. So you know, it resembles it, but what is in solution is bigger than just this thing. So, but you can now adjust this PDB, adding, you know, dimers and heteromers or whatever, and try to find some PDB structure that you built that more resembles what you've measured in solution. And obviously you don't have protein 2 here, but anyway. That's how you'd work back and forth. All right, with that, Mikhail is chomping at the bit.
That protein structure is only a part of the molecule. It's not the entire molecule.
Right, so you'd want to build in the other parts and start trying to assemble it.